Good day and welcome everyone to today's webinar called What Grades of Electrodes are Available for the Most Severe Environments. And the presentation will be provided by Peter Stones, who is working with the business development of our specialty alloys range in Europe. And my name is Tapio Huhtala, and I'm working as a global product manager for the specialty alloys electrodes within ESAB. After the presentation, there will be a brief Q&A session. So in case you have any questions, please send them through and we will review and address them after the presentation. So please, Peter, the stage is yours.
Thank you, Tapio, and good afternoon, everyone. Thank you for joining us. As Tapio said, the topic of this one is the covered electrodes for the most severe environments. It's a brief snapshot. It's a bit of a taster to give people enough information to ask more questions if they wish to. As Tapio said, there's a Q&A box. If you ask your questions via the Q&A panel, we're more than happy to answer if we can, and if we can't, we'll get back to you. The only other thing to say really is that there's no need to take notes or anything. This presentation is being recorded. It's available on our YouTube channel, the ESAB University YouTube channel, and mine and Tapio's contact details are available at the end. Should you wish copies of these slides, then by all means drop us an email and we're happy to send copies of the slides. If you have any questions that you think of subsequent to after we've finished, please drop us an email again and we'll do our best to answer them. So on with the show. The reason for this one, really, I've been asked to put this one together is because the covered electrodes are not generally considered for some of the most severe environments. Solid wires and maybe metal cord, flux cord wires seem to be more prevalent, and I think people are forgetting that there's a huge industry out there and a huge product range that are absolutely designed specifically for these types of environments. So what I want to discuss is what are some of the most harsh, most severe environments for fabrication, and what factors affect the corrosivity of the media, which grades of electrodes are available on the market that are suitable, being specifically designed for these types of work, and are there any new ones? Is work still being developed? Well, we're ESAB, so not surprisingly, yes. The answer to that is yes, and I'll let you know what the electrodes are that are very, very recent developments. And of course, we're a welding company, so we'll talk about weldability. How easy are they to weld? So just using really as an example some of the harshest environments, I want to talk about this group here: sulfuric acid, chlorine, hydrochloric acid, urea, nitric acid, and phosphoric acid. They're all very closely related, and the amount of business in these types of products is absolutely huge. So if you're driving past any kind of chemical works with lovely stainless steel piping and tanks, then if you're not entirely sure what they're doing, then there's a good chance that they'll be involved in this kind of business. It's exactly the right sort of business for these type of products. So talking about this range: sulfuric acid, chlorine, and hydrochloric acid. So sulfuric acid, and the way that it's manufactured, I'll describe briefly in the next slide. But the number of uses, or rather the worst environments for that we can think of, really. Sulfuric acid is massive. There are millions of tons of sulfuric acid produced every year, and sulfuric acid in various forms mixed with water is very, very aggressive. It's a very, very aggressive media. Hydrogen chloride, again, mixed with water, becomes hydrochloric acid, and they're all very closely related in terms of the production. So these are kind of the things that we want to focus on. Again, just used as a snapshot. So in terms of why is sulfuric acid such a big product, such a large volume product in the world? And more than half of it, and it's 200 million tons of sulfuric acid are produced every year, and more than that, more than half of that is used in the production of chemical fertilizers. So you start with sulfuric, so you produce sulfuric acid, convert that into phosphoric acid, and that's subsequently used to make phosphate or chemical fertilizers. Fertilizers are a massive business all over the world, and we're talking millions of tons. And still, while battery technology is changing rapidly, there's still an awful lot of the old-fashioned lead acid batteries around in the older cars and lorries. And the electrolyte in there, the liquid that's sloshing around in there, is sulfuric acid. So again, there's millions of tons required. The other big use, really, two big uses rather, is for in iron, copper, steel works. Because sulfuric acid is so corrosive, then it's an excellent pickling agent. So it corrodes the surface, it cleans the surface prior to any subsequent further coating. So again, you can imagine that steelworks need a considerable amount of volume. The other big use is for petrochemical refining. So the sulfuric acid is used actually as a catalyst involved to remove impurities out of the various stages of crude oil refining. So again, huge usage. And the last one at the bottom there is why it's so closely linked is manufacture of chlorine. And chlorine again is a huge industry all in itself. I'm sure everybody's heard of chlorine, probably with chlorinated water and swimming pools. Chlorination of water drinking supply was done 100 years ago. It started 100 years ago in America, New Jersey, and obviously chlorine is a bleach, and it's still used for this type of application again. So in terms of industrial use, chlorine is a bleach. It produces bleach, so a bleaching agent, so anything that needs to be bleached. And paper and pulp industry is the big user of this massive business for chlorine, chlorine producing bleach, and the bleaching of paper and pulp, and obviously textiles as well. It is a strong antiseptic disinfectant, so all the antiseptic disinfectant products generally will contain some amount of bleach in there in some form or another, some form of strength. I've mentioned water and swimming pools, and obviously it's a strong bleaching agent, so dyes, plastics, pharmaceuticals, big uses. So the production of chlorine is very closely linked with the production of sulfuric acid. In terms of manufacturing, you can see the schematic here. I've mentioned it's already 200 million tons per year, so it's an enormous business, and all of these kind of fabricated products occur pretty much everywhere. So superheaters, converters, heat exchangers, if you can imagine, all of these have got to be produced to be able to withstand sulfuric acid. So it's manufactured by converting SO2 to SO3, adding water. I'm simplifying this very considerably to produce the sulfuric acid. So the raw material is sulfur dug out of the ground, or pyrites as it's called. That's burnt, and that's what forms the SO2. So that's what's further processed down to make the acid. So it's a massive business. And all of this equipment, the process equipment, needs to be suitable to withstand the chemistry. In terms of a corrosion diagram, it's a nice illustration, really. So this is a proprietary diagram that's from Sandvik. So not surprisingly, there are Sandvik grades listed on here. So what this illustrates is a decay rate, a corrosion rate of 0.1 millimeters a year. So this material, SAF 2304, so it's a lean duplex. If it's immersed in sulfuric acid at a weight of 20% at 20 degrees, then it will last 1 year before it decays 0.1 millimeters. So if you cross that line, you go over the line, then it's going to be more than that. So it's just a nice illustration really of we've got the same, it's the same amount of corrosion. It's 0.1 millimeters per year for lean duplex. You can see this is 2205, so this is a duplex grade. So you can see for the same amount of wear, it can withstand it at a higher weight, a higher strength of acid, and at higher temperatures. And again, this is super duplex 904L. So interesting. And these are these type of corrosion diagrams are what used in the design of all the process equipment that we saw in the previous slide. In terms of the choice of materials, then it's quite vast. And again, this is really just an illustration. It's not a complete and comprehensive list of every filler metal grade or electrode that's available. It's a fairly comprehensive list. So what it's illustrating again is the strength of acid. So if you have acid, the sulfuric acid, that's less than 10% strength, and it's less than 40 degrees, then even materials such as standard austenitic stainless steels like 308 and 316 are suitable. So they're suitable for the fabrication. And obviously we've got solid wire filler grades as well as electrodes, the topic of this this webinar. And obviously if you increase the temperature, you increase the strength and you increase the temperature, then basically the alloys get higher, the amount of alloys in the base materials, the solid wire fillers, and subsequently the electrodes. So what I'm trying to illustrate here really is the amount of electrode grades that are available and more than suitable to coincide with, to complement the solid wires. So you know, even up to 80 degrees, for example, we can use things like 385, 383, and these exist in both solid wires and also in covered electrodes. So these are very high alloys. This is 27 chrome, 31 nickel, 4 molybdenum with low carbon and with copper. So it is available as a rutile electrode, for example. Similarly with 380, 383. 2025-5 LCU or an OK 6933. So these are still, we're still using stainless steels at these kind of levels, and it's only when you get up kind of above 50 degrees, so you're getting over 20% strength and over 50 degrees, that we need to start using the nickel grades. So again, the nickel grades and zirconium, of course, but nickel grades of base metals. There's a large range of nickel-based solid wires to match the accompanying base metal. And again, there are also electrodes as well. So these are very highly alloyed with nickel, but they're available in covered electrodes. Once you get into above 70%, then things get a little bit more scary, and surprisingly we've got duplex and super duplex in here. So we have duplex and super duplex covered electrodes as well. Above 98% strength and 60 degrees, then there is only one option and there's no electrode. So this is SX, it's a Sandvik proprietary product that's available from ESAB. In terms of weldability, there's things to be taken into consideration really. Then this is a phase diagram showing the modes of solidification depending upon the grade. So this scale up here really is this chrome equivalent, nickel equivalent. So these are formulas that are determined by the composition of the filler metals. And what we're trying to illustrate here, it's an old diagram. The solidification that you get, depending upon the chemistry, can either be fully austenitic, for example. So we've got a fully austenitic, so there's no ferrite in there, compared to the other end of the scale, if you like, where you've got fully ferritic. So all of this is austenite and all of this is ferrite. And then in between, you've got either transformations from austenite to ferrite, a mixture of the two, or from ferrite to austenite. In a brief nutshell, the presence of ferrite, there's more room, if you like. It's the best way to describe it. The ferrite lattice is wider than the austenite lattice, and so there's space to fit in impurities. So this is a big thing, obviously, with welding. If there's room to fit impurities in there, so anything with ferrite in there is less forgiving. The fully super austenitics, the solidification mode is primarily it's austenitic. So there's no phase transformation in there. It's austenitic, and there's no room for ferrite. So there's no room for any impurities to be dispersed or to be compensated for. And this has to be taken into consideration. So it affects, this is the chemistry behind what's happening when you're welding. Segregation is another thing. Then, for instance, if you're not careful, then there's if you do a cross section across the weld, then the concentration of something like molybdenum varies considerably. So this is an average, but it varies up and down the scale. Again, this is something to take into account, and it's dependent upon the chemistry that you're welding. It's dependent upon the chemistry of the base metals, and also the parameters on how you're welding it. Similarly, mixed modes of solidification. So within the same weld, you can get the ferritic solidification mode mechanism with austenite in it, or the austenite with a little bit of ferrite in it. So again, these are very high alloys, and these are the kind of effects that can have during welding. I'm trying not to get too bogged down. This type of hot cracking is easy to reproduce in something like a super austenitic. So where there's no ferrite in there, as I mentioned, ferrite, the ferritic structure has gaps in it that can compensate for any kind of impurities. So if you have a super austenitic that has zero ferrite, then it's not very forgiving for impurities that are in there. There's a number of things that you can do to influence it, but essentially the weld doesn't have strength to hold itself together as it's cooling down. So the thermal stresses that are induced by cooling down, by heating up and cooling down, are more than the mechanical strength of the weld, and that's why it cracks on cooling. But I've got to stress, yeah, it is really with the super austenitic, so the very high alloyed grades, super austenitics, the nickel alloys, that kind of thing. With standard austenitics, this is not generally an issue because of the presence of ferrite. So as a quick, as an easy and quick kind of guide, we're trying to make the bead shape convex. So there's enough material in there to compensate for the lack of strength, if you like. You're waiting for the bead, you're waiting for the weld to cool down and have enough strength to hold itself together before it solidifies. And so the ways to help are to make sure everything's clean. Obviously, it's a stainless steel. The higher the alloy, the more problems there are. but keep everything clean. The bead shape is important. Thermal stresses, so welding sequence is important. Don't put all the heat on one side. For example, it will crack. And the filler metal choice is an obvious one. So in terms of the range, there is a vast range. Again, this is not a full and comprehensive list of everything that's available, not by any means. But all of these, every single item on here is a grade of electrode that are suitable for some part of the processing of sulfuric acid production, or urea production, or chlorine production. Generally, as we go down the scale, they increase in alloy content. So we have a big range of both stainless, including duplexes and super duplexes, and we've also got a very large range of nickel-based alloys. If you recognise some of the nomenclature, nickel chrome cobalt moly 1, nickel chrome moly 3 is the common one, or alloy 625 equivalent. But we have a vast range in the portfolio, so all of these are available and are very commonly used in the worst and most severe environments. And last thing I'll leave you with are two brand new grades, as I mentioned. So these are brand new. We've got an Ni60 LFE. So this is a nickel chrome moly 3, alloy 625 equivalent. So it's a 60% nickel. So in the same way that that grade is suitable for welding nickel-based alloys, 5%, 9% steels, 254 Ma. The key with this is the LFE means it's low iron. So we've got an all weld metal content that has less than 1% iron. So in terms of cladding, there are benefits. Certain companies insist on specifications and classifications that insist on low iron content in the nickel weld overlay. So we have this grade available now that's low iron. And the second one, again, it's another derivative of the 625, so it's a nickel chrome moly 3. This is nickel chrome moly 3P, so very specifically designed for all position welding. So this gives a much better quality of weld, and it's easier to weld in all positions, including overhead. So whereas some of the grades previously suffered from being not very friendly to weld in all position and maybe giving a little bit too much porosity, this one's been specifically designed for all positional, overhead and low porosity welding. As I said, that's mine and Tapio's contact details. If anybody has any questions, please drop us an email. If you think of anything, if you think we can help in anything to do with specialty alloys, stainless, nickel alloys, not just electrodes, but any kind of filler metal, please feel free to give us a call or drop us a line. So that was 25 minutes. Tapio, any questions?
Yes, we have actually received a few ones, so let's start. Okay, you list several different grades of duplex 2209 and super duplex 2594 under the ESAB brand. So what are the differences? Yeah, because we do have the OK electrodes available as well, and then we also have the Hexaton. And they are not identical. If we, for instance, look at the duplex, the 6750 type, it's the acid rutile, and the Hexaton version. The ESAB one is more of a synthetic type. while the 2293 we use a fully alloyed core wire for that one. So the slag detachability, etc., is better for the hexaton version. If we look also at the super duplex types, the basic one, the 6855, that is also more of a synthetic type for the ESAB, while it's we use a fully alloyed core for the 2510-4 LB. So if one aims at the highest possible corrosion resistance and so on, one can use the hexaton range. But it's also worth mentioning that for the super duplex, the basic one, the 2510-4 LB is more prone to form pores than the 6855 and so on. So in case one has a requirement of porosity-free welds in unwrapped position, it's better and safer to use the OK6855 electrode.
Good, that's clear. Yeah, sure.
Okay, then we have another one. It says, yeah, is the hexaton nickel 60 low iron available? And yeah, I can answer to that. That yeah, we have launched it. It has been a regional launch. And we have seen that kind of requirements with very low iron contents at the top of claddings in other regions, like in Middle East, India. We have also seen it in Asia, but so far we have not really seen that kind of requests and so on in Europe. But our intention is, of course, that if we start seeing that kind of demand and so on also in Europe, that we will make it available.
Sure. So the development of it was driven by the Indian market, was it?
Yeah, it was driven by the Middle East and India market.
Okay, right. Yeah, fine.
And yeah, I think we also have a final one concerning the nickel chromoly 3P. That when will that be available? And we are working on that. The item is, we are working on getting the items live in our systems and so on. So the product and so on will be launched within the nearest future. And our intention there is also to make it available for European market and so on from the beginning.
Great stuff. Yeah.
Okay. Okay, then we also have another one. Why is OK6120 in the list? It is barely available while 6130 is. Yeah, well, the 6120 is still available, but yeah, and it is a special electrode for welding thin pipes in vertical down position. It is very similar to the 6320, which is also used a lot within the paper and pulp industry. So,
okay.
Yeah, so the consumption and usage and so on is, yeah, for those very specific applications. So if you weld in other positions and you need higher deposition rates, the 6130 is the proper choice for those applications.
Clear. Thank you. Yeah.
Okay, I think that's all. No further questions.
No. So thank you very much. The next presentation will be the usual time of 1:30 in the afternoon. This one's been a bit early today. It's on Friday the 21st, and there's a number of topics that are fighting to be taken, and we haven't chosen it yet. But watch this space. If you've registered on the form for this webinar, then you'll receive reminders about the next one, and full details will be included in that. So thank you very much, everyone. Have a nice weekend.